Okay, good afternoon, everybody. Welcome to the IWF seminar. It's my pleasure to introduce to you Daniel Schmid. Daniel came to IWF in 2009 when he came to his senses that space plasma physics is much more interesting than solid state physics. After he talked with Rumi and me, we decided to give him a project on magnetotail dipolarizations, measuring with the cluster mission, and he did a pretty good job in his master thesis and wrote a paper about that immediately got cited an awful lot of time. So we decided, okay, we can give him a PhD position. So I tried to get money from FWF, and then that got lost in FWF, and so we had to wait over a year before we finally got the money for his project. But then he could continue his work on dipolarizations and did a successful thesis about that. Then he stayed here a little while, and then we kicked him out, and he went to China. And Tilong made sure that he arrived at the right place in Shenzhen. He worked there for 3 years and then came back here to IWF, where he then decided to work on the BepiColombo mission. And as things developed, everything goes well. And then Johan finally retired completely and gave the PI ship of the magnetometer of the MEO spacecraft, so the Japanese spacecraft, over to Danile. So this mailbox is a little bit cooler now than it already was. And now he's going to tell us something about what MESSENGER measured at Mercury, and maybe also how BepiColombo is going to do that much better. But I'll leave that to Daniel to explain, and the floor is yours.
Okay, thank you very much, Martin, for this nice presentation. You guys can hear me in the back? That's good? Okay, perfect. Yeah, regarding the BepiColombo, probably we won't have time to dig or dive deeper into BepiColombo. So today, only messenger data. And I'm very happy actually to present this topic where we reported last year, we published this in Nature Communication on the first detection of atomic lithium in the space environment around Mercury. As you can see here from my co-author list, it's actually a joint study between the space plasma group as well as the solar system group. And I'm very happy actually about this work because it shows how different groups within the institute can work together and develop really great science. And but we will come to this later. All right, so this, just as a reminder, this whole talk is more kind of a very fundamental talk, introductory talk. So if you have questions or anything is unclear, please just interrupt me, and I'll try to explain and answer your questions indeed. So, all right. So Mercury, as we know, is the planet that is closest to the sun. That means, and we have Mercury, Venus, Earth. So Mercury is within the inner solar system. And until the 70s, it was not known that Mercury actually possesses an exosphere. An exosphere itself, compared to Earth, here at Earth we have a dense atmosphere, also an exosphere, where we have an exobase, and the exosphere is characterized that these particles are actually gravitationally bound to the planet itself, but have very few collisions. That means each of these particles travel on a ballistic pathway and do not collide each other. So this is how you define an exosphere. And at Mercury, this exosphere is actually this, the exobase itself is the surface. So pretty much similar picture like we have here on our. So there are various source processes that actually the particles in the exosphere can originate from. So for example, there are low energy processes such as photostimulated desorption. That means we have the radiation from the sun. And if this radiation is strong enough, or the photons are strong enough, that the binding energy between different elements or molecules on the surface are overcome, then these particles get released and desorbed into the exosphere. Another mechanism is the thermal evaporation. That means if the temperature is high enough, those particles are just thermally released from the surface itself. And just to mention this, so Mercury is a planet of extremes. Due to this close proximity to the sun itself, we have average dayside temperature of 450 Kelvin or even more. And on the night side, on the other side, we have, since we do not have a dense atmosphere, the heat cannot be kept at the planet, we have temperature of minus 180. However, thermal evaporation is also one of these source processes the elements can come from. Besides these low energetic processes, there are also high energetic processes, high energy processes, such as ion sputtering. Ion sputtering means if we have energetic particles, like energetic solar wind particles, particles coming from the magnetosphere through magnetic reconnection accelerated, these particles can hit the regolith, so the surface, and kick out the other particles and end up once again in the exosphere. And finally, there is also the possibility of meteoroid vaporization. That means, like at Earth, the Mercury is actually continuously bombarded by a kind of micrometeoroids all the time. It's very similar to find here at Earth. And these meteoroids can vaporize, not only eject the material within the meteoroid, but also from the surface material. And so lots of material can be released from the Hermian regolith. All right, so far, the exosphere has been studied mainly remotely. That means we have a line of sight, and along this line of sight, we specifically look at the spectral lines of different elements and characterize or identify these elements. So the first mission, as I mentioned before, Mariner 10, this was in the 70s, was a mission that had 3 flybys in total at Mercury itself. And this was in between 74 and 75. And during these flybys, Mariner 10 not only detected an exosphere, so the existence of hydrogen, helium, and oxygen, but also that Mercury possesses an intrinsic magnetic field. So this is pretty interesting because our twin planet, Venus, for example, or Mars, they do not have an intrinsic magnetic field. Mercury has. Why? So this is one of the key questions BepiColombo is also after. But this is a different story, so maybe another time. So anyway, Mariner 10 was the first who discovered or detected such an exosphere and found those elements. Later, in the 80s, telescopes, ground-based telescopes, found also sodium and calcium elements. Why in the 80s? Because there, these telescopes were strong enough and good enough. You need to imagine just a few words that Mercury is very difficult to observe. Because Mercury is between Sun and Earth, so in the inner heliosphere, we only have a very limited time during the day where we can observe the planet. And this is just before dawn and after dusk, when the sun just sets down. This is the only time, because during night, of course, we are looking into the outer heliosphere, and so there is no Mercury around. So anyway, from this ground-based telescope, we found sodium and calcium as well. And then later, there was a second spacecraft mission to Mercury, and so far the only one. So BepiColombo will be the third one. This was NASA's mission Messenger. So this mission launched in 2008. And between 2011 and 15, the mission itself, or the spacecraft itself, was in a highly elliptical orbit around the planet, so a polar orbit, where the periapsis, that means the closest distance to the planet, was kind of 200 kilometers. The apoapsis, so the distance farthest away from the planet, about 15,000 kilometers. Complete orbit of this spacecraft took about 12 hours. And this mission probed Mercury for 4 years, so 4 Earth years, I need to say, because 1 Mercury year is kind of 88 days, because this planet is pretty fast around the sun. Okay, and important things to mention. So messenger also detected mangan, helium, aluminium, iron, and mangan itself. So magnesium, sorry. And if we have a look here on the periodic table, so the first two groups, so the alkali and alkene elements, we see that we find actually lots of them from this ultraviolet spectrometer or remotely detection of these elements. So we find sodium, magnesium, kalium, calcium, also aluminium, but we care about this one. So a long time, it has been speculated that if we find those elements, unfortunately, pointer is not working.
Okay, the battery.
So,
Okay, there's another one.
okay.
Perfect.
Yeah, much better, thanks. So it has been long and widely speculated that also lithium should be existence in this exosphere. However, up to date, this, oh no, this is not working now. Just change it. Sorry for the interruption. Any questions?
What's the voltage of the battery?
I was the speculation about beryllium. Why?
Beryllium, actually, there is not much beryllium around. So, sorry?
Why do you know?
I don't know, but from the existence, I would say, so I'm not a chemistry guy, but I guess beryllium, the abundance of beryllium is very low compared to lithium or sodium.
Lithium is easier to detect spectroscopically. Helium maybe there also, of course, and all elements maybe there, but.
Okay, so once again, coming back again. So it has been speculated lithium should be in the exosphere around Mercury. And here we now present the first evidence that it is so. The question is, why haven't been observed in the previous measurements of remote sensing? The reason is because the lithium content is very, very low, and in situ measurements on board messenger couldn't actually resolve this particle species. And the second reason for the remote one, the same. There is too less lithium around that we really get nice spectral lines regarding the lithium. The first evidence on a completely different approach. So we used indirect observations from so-called pickup ion cyclotron waves, short ICWs here, which are based on the magnetic field measurements. And how did we do this? But before we do, maybe step by step, what is a pickup ion cyclotron wave? So here, once again, we see the space environment around Mercury. So Mercury here, on the left, we have the sun. The sun, actually, we find the solar wind actually leaving from the sun. So going to the right towards the planet, embedded in the solar wind. So VSV is the solar wind velocity. Embedded in this highly conducting solar wind plasma, we find the magnetic field of the sun, so-called interplanetary magnetic field. So, and as this supermagnetosonic wave approaches Mercury, I mentioned it before, has an intrinsic magnetic field. That means this is an obstacle for the supermagnetosonic wave, so a bow shock emerges ahead of this. And the exosphere of Mercury reaches way out into the interplanetary space, into the solar wind. This is also an important point we will see in the next couple of slides. So we have, for example, we have an exosphere containing some neutral species, let's call it X. So this neutral species is here in the solar wind somewhere. It's neutral, so it's not affected by the solar wind at all. So we do not have collisions in the solar wind. The mean free path is extremely large, so no collisions. So these particles are just floating around. And then a photon from the sun, solar UV radiation, photoionizes this particle. What happens is that the electron is kicked out. So we have an ionization of this neutral particle. It gets charged. And immediately when it gets charged, the Lorentz force actually kicks in. That means charged particles moving in a magnetic field is forced on this gyro motion around the magnetic flux or the magnetic field due to the Lorentz force. And in the next step, these picked up particles are injected into the solar wind. So you need to think of these particles are sitting down there in the interplanetary space, and then the solar wind with 400 kilometers per second is coming. These particles are very slow. That means in the reference frame of the solar wind, these particles just appear from nowhere, because before they were neutral and didn't interact with the magnetic field. Then they got ionized, immediately appeared in the solar wind. So the solar wind actually picks up these particles. And this angle alpha is the injection angle or the pickup angle under which these particles get picked up. That means we inject these particles. So if we change now in the reference frame of the solar wind, so I'm sitting in the solar wind, everything is nice, a couple of particles faster, a couple of particles slower, and now I see 400 kilometers per second particle coming towards me. These are these injected particles, or these pickup ions. So these pickup ions will actually move along the magnetic field lines, and by doing so, they curate and form a helical spiral along the magnetic field. So you have unfortunately, I couldn't draw this in PowerPoint, but you can imagine. So these particles curate around the magnetic field and make this kind of helix spiral configuration. And this configuration of these pickup ions, as mentioned before, so these are suddenly here, and give a secondary distribution in the velocity space. That means in the solar wind, we have kind of a Maxwell distribution. Let's assume we have a Maxwell distribution, and then suddenly beside we see this very energetic beam of particles with 400 kilometers. The solar wind now to equalize all this stuff again. So we need to get rid of this surplus of these injected particles via resonant or also non-resonant instabilities. I don't go into detail, this, otherwise we would sit another 2 or 3 hours. But what happens is that the solar wind becomes unstable and the energy is actually released to the wave, and we have the excitation of this so-called pickup ion cyclotron waves. This is in principle how this scenario works. But let's look a little bit deeper into this. So what are the properties of this pickup ion cyclotron waves? So if this resonance condition holds, that means, once again, we have here our pickup, also ionized particle, curating around the magnetic field with some Curie frequency omega c, and moves along this magnetic field, so the interplanetary background magnetic field.
Is it moving along or is it accelerated?
It depends on the frame where you look at. So here we are now in the solar wind frame. So we are sitting in the solar wind frame, and now this particle comes with 400 kilometers per second towards us. If we sit in the planetary frame, in the particle frame, then the solar wind is coming with 400 kilometers per second. So right now we are in the solar wind. Okay? And in the solar wind frame, particles that have a specific gyro frequency omega c, including a specific velocity parallel to the background magnetic field, can excite or can be in resonance with plasma waves in the solar wind, with background solar wind or magnetic field, with frequency omega and wave vector k. And how can you think of this? So we have this, the particle curates around it, and so here I illustrated roughly how this picture looks like. So we have kind of the particle curating around it, and in this way, wave is actually excited. So getting the energy from this injected particle and transfer it into the wave power. So we can also think of this, that if the particle makes one duration around the magnetic field, we always see exactly the same phase of this plasma wave. So we are actually phase locked to this. This is what the resonance condition tells us. So if this is fulfilled, then waves in the plasma, in the solar wind rest frame once again, emerges with a specific frequency and K. And now let's change into the spacecraft frame. So basically into the planetary ion frame. So that means the injection velocity, so from before, the injection velocity, which is just opposite to the solar wind velocity, changes. So we go in this direction. And that means this wave, we assume now this wave is already excited. And this wave has maybe a small note beside this. This wave has a phase velocity, so that means the velocity the phase propagates along the magnetic field of kindly in the upper limit the Alfvén velocity. And this velocity is much smaller than the solar wind velocity. It means these waves are basically frozen into our plasma and tracked along with the solar wind. So we have this moving thing, and then this moving thing is going in this direction all the time. So in our spacecraft here, we would have observed this wave Doppler shifted. And Doppler shifted, here the normal formula. We have the k vector, k parallel times the solar wind velocity. This gives us the Doppler shift of this plasma wave. Is in this, and in the spacecraft frame, we observe then this frequency. And if we now look at this dot product between the k parallel, the solar wind from our Doppler shift, with this resonance condition of k times the parallel velocity, this is exactly the same, just with a minus. And so in the spacecraft frame, we will observe this specific type of wave always at the local GEO frequency. And this is a very important point. Actually, the only point you can forget about the last 5-10 minutes. The most important point is in the spacecraft frame, we observe this always at the local gyro frequency. And now we see something, because this gyro frequency is defined by the charge, magnetic field, and mass. And this means basically based on our magnetic field measurements, together with this specific frequency of the wave, we can determine the Q to M ratio. And in this way, the magnetometer can act as a particle spectrometer. It's pretty cool.
Maybe you said it and I missed it, but what is the physical reason for all the particles to be in phase? Because this is for one particle, very good, and then you have another one, and it could start at a different phase.
So if we go into this, then we need to go into kinetic theory. This would be a little bit more. The thing is this, you have a distribution of all of these particles itself. And so many of those particles get ionized all the time, continuously, picked up by the solar wind. And in the solar wind itself, you have, solar wind is not the laminar stream of particles. So you have kind of tiny fluctuations within the solar wind. And some of these tiny fluctuations are just in resonance with this emission. And these tiny fluctuations are then excited and the wave can grow. Maybe this picture helps a little bit more.
A very probably naive question. So what kind of wave is this? I mean, if we speak, then we have a pressure wave, right?
Not a pressure wave.
I do understand that one, but what is the physical property that actually has it?
Okay. Thank you very much for asking. So the physical property of this wave, so we have fluctuations perpendicular to the background. That means these waves are transverse waves. So not a compressional wave, longitudinal, it's a transverse wave. So the fluctuations are really perpendicular to it. So this type of wave is an electromagnetic wave, so to speak. And this wave have also a kind of a polarization. So they are circularly polarized. So there are two modes. You can have either left-handed polarized or right-handed polarized waves. And typically, from kinetic theory, we know that for this kind of instability, this is also called the ion-ion beam instability. For this kind of instability, the right-handed mode is dominating. So this wave itself is an electromagnetic wave propagating along the magnetic field line. A transverse wave, this means the fluctuations are perpendicular to this. So like we know from electromagnetic waves. And the polarization of this wave is not like here in the drawing, it's kind of a linear wave going like this. It's not, it's going actually like this. It's a circular one, right-handed circular one. This answers your question. Anyway, based on these properties of the Bickert-Dine cyclotron wave, we now surveyed our magnetic field data once again, and specifically looking at lithium. So for this Q to M ratio, we just inserted lithium, had a bunch of magnetic field data, 4 years of magnetic field data, and then applied a selection criteria, which in the following I will explain, onto a 200-second sliding window. So we really went manually through this, not manually, but automatic through this massive data set. One of the selection criteria is that we have these strong fluctuations around the lithium gyro frequency. As mentioned before, we just gave the mass of it. We assumed singly charged So here you have the Coulomb charge. And then we got this frequency, and we applied actually a frequency range around this. This has something to do with the nature of these waves. Without going too much into detail, you have kind of the peak of this wave is not exactly at the gyro frequency. It's a little bit below the gyro frequency. And the reason for that is that these waves are not purely parallel. They are slightly under angle to it. So this comes also from linear theory. But anyway, so we applied this kind of frequency range, so 80% below the gyro frequency to the gyro frequency, and looked if we have here strong fluctuations in this frequency range. For the perpendicular fluctuations, we required, so we changed from the temporal time series into the frequency domain, calculated the power spectral density matrix, and then we estimated the ratio between transverse to the parallel component. So here, this is the compressiveness of the wave. This is how transverse the wave is. And we require that this wave is very transverse. By a factor of 5, this incompressible part needs to be larger than the compressive one. And finally, also for this circular polarization, we gave a requirement, and the polarization of waves we can also determine here from the cross-spectral density matrix. Maybe another time we have time to talk about this in detail. But a parameter where you can find this kind of polarization is the ellipticity. A minus sign means left-handed, plus sign means right-handed. And 1 means completely circular, that the wave is really like a circle, looking from behind or from above. And 0 means linear, that the wave is just going in this direction or just a linear polarization. So and now you can ask, moment, you just said these waves have a right-handed polarization, and here we go for left-handed waves. The reason for that is once again the fact that the phase velocity of the wave, so the speed the wave can travel, is lower than the solar wind velocity. So basically the wave travels along the magnetic field line towards the sun, but at the same time is dragged with the solar wind. It's frozen in the plasma solar wind going back. So that means this right-handed circular wave moving in the reference frame of the solar wind is actually unwind, going backwards. So left-handed, observed in our spacecraft frame. And all these measurements are in the spacecraft frame itself. Okay, so based on this selection criteria, here we have actually the first indirect evidence of such lithium-ion cyclotron waves. So it looks a little complicated. Let me guide you through this slide. So in the top panel, we have the magnetic field. So the magnetic field data, X, Y, and Z, has been transformed in the so-called mean-aligned coordinate system. In this, we go from the planetary coordinate system just into the background magnetic field direction. So one axis, here the green axis, is pointing along the magnetic field, and the red and blue ones are perpendicular to the magnetic field. So we calculated the average background magnetic field, turned it in, and then we had 1 parallel component and 2 perpendicular components. And we see it here. So indeed, we see the strong fluctuations here in the perpendicular components. We see that both of these perpendicular components are in quadrature. That means the phase between these 2 perpendicular components is very stable throughout this time interval. The wave itself, we analyzed it here in the frequency domain. So this is the power spectral density. The red line gives us the transverse power. The green line is the compressional power, and within the frequency domain, delta F, so here from our selection criteria, so the local gyro frequency, we see that we have this peak indeed within this frequency range itself. And here in the bottom right, in panel C, once again, you see kind of the so-called hodogram. Hodogram just plots the 2 perpendicular components in the middle against each other. And this means basically that the background magnetic field is pointing outward of the wall towards you guys, and the rest, the 2 perpendicular components, describe indeed a left-handed circular wave.
In terms of the ratio Q per M, how far the other frequencies for other elements are close to this peak?
Not very close. So this is one of the point. Of course, we are limited to the Q/M ratio. So it might be that something is charged doubly and the mass is just half of it or whatever. So sometimes you get in this range. For lithium, you're not. So not even close with other elements. This is the good thing. Yeah. So we can be pretty sure if indeed is lithium.
Daniel?
Oh yeah.
How significant is the peak here? Because anything at 10 to the minus 2 close to DC, I would not trust so much the power spectrum because you only have like 5 points or 2 points or whatever.
Yeah.
And it's hard to distinguish when it's so close to DC, right?
Absolutely. And yes, this is an old plot I gave here. you trapped me because this was also one of the questions from the referee. So once again,
You refer it.
yes. So once again, we analyzed this data set. So here we have the 200 seconds plotted, but we took just a longer time interval. So we have a higher temporal
Lower frequency, and then you can see the peak better. Or
You just, no, not this one, but you have just more data points. So this, of course, gives you a, yes. Okay, and for our study, we only considered once again, as we can, I will mention in 5 or 10 minutes, how much time we have?
15.
Okay,
15 minutes.
this is good. And end up in total with 20 time intervals where all of the selection criteria plus additional selection criteria, I do not go into detail, give us 20 time intervals. Of course, like in this example here, some of the time intervals go also to previous or to later moments. That means this is actually one event, but we just artificially divided it into 2 due to the limited size of the selection window. So in total, we actually find 12 unique independent ion cyclotron wave events. Okay, and so we thought, okay, detecting of lithium, pretty cool, but what can we do with this? So we started digging deeper into theory. Indeed, there are studies back from the 90s where you can actually estimate from the pickup ion observation, from this wave observation, the lithium density. So from Huddleston, Debbie, and Johnston in 92, there we have this very, I would say, simple formula to estimate the free energy from, or let's phrase it different, the total free energy available for this wave growth itself, available from the wave growth and coming from the pickup ions is given by this formula. So the more pickup ions we have, the more free energy we have, basically. And if we go now one term after the other, so this is the free energy that is available for the wave growth itself. N is the pickup ion density, the mass we know, of course. VA is the Alfvén velocity. So this is the upper limit of this phase velocity of this traveling wave. V injection is the injection velocity of this pickup ions. And alpha is the angle under which we picked it up. So the free energy, actually, we can obtain. A simple trick. We go back to our power spectral density matrix, have here our frequency range, and we know that these incompressible part, transverse parts, we integrate over the frequency, we get basically, of course, there is a 2 0 missing, but forget it. Basically, from the integration, we get the power of the wave itself. And now this wave power comes actually from the fact that we need to have somewhere free energy, otherwise the wave cannot grow. But not all of the free wave for free energy is transferred to the wave itself. Only if this efficiency coefficient would be 1, then we know, good, we have these pickup particles, and they transfer the complete energy to the wave. In this case, the efficiency coefficient would be 1. In reality, this is not the case. And in fact, computer simulations show that the pickup ions lose about 30% to the wave group. So for the phi, we have a factor of 0.3. The rest is going to heat, dissipates, wherever. Anyway, from our observation of the magnetic field, perpendicular fluctuations, we obtained a value for the free energy. Good. So we just need to calculate the Alfvén velocity given by the background magnetic field, and the square root basically of the solar wind density. And the injection velocity is just minus the solar wind velocity. So if we have all these plasma parameters, we could easily calculate it. Unfortunately, the plasma instrument is sitting behind the solar sheet here, which protects the spacecraft from the hint, from the sun itself. But that means if we are in the solar wind, of course, the sun is just behind us, the solar wind. It means we have just a very limited field of view of our particle instrument. This means in turn that we have just limited amount of data from the spacecraft itself. And in fact, we checked this for these 12 events. We do not have plasma data. So these values might be just not known. But there is another possibility. And what we did is actually we used a solar wind propagation model. So this solar wind propagation model from Tao et al. Just uses observations from the sun from Earth and then calculates into the solar activity and other parameters they obtain from observation a complete solar wind propagation model throughout the entire heliosphere. And from that point, we actually get the solar wind velocity as well as the density at the position of Mercury during the event detection. So in fact, we can actually calculate this value. However, one more point. So not only the solar wind, due to the close proximity of Mercury around the sun. So Mercury is super fast around the sun, like 50 kilometers, even more, 55 kilometers per second around the sun. Kepler's law, of course, compared to Earth, 30 kilometers per second. We actually need to consider this fast movement of the planet itself, because we have kind of 400 kilometers and 50 kilometers from the planet itself. And we are in the reference frame the rest frame of the planet. And so we need to consider this aberrated solar wind velocity, because this is very important, in particular later for the injection velocity here, so that we get the right angle. So we took the data from the navigation and ancillary information data set and just plugged it in and calculated the injection velocity as well as the injection angle here, once again illustrated in this plot. Okay, so now we have all of the parameter, just rearranging this equation, we get the pickup ion density. Nice. So this is the first step. So we get an idea how many ions are there at the observation location where we are at. However, more interesting, particular for planetary science, is what about the neutral particles? So in fact, if we consider a quasi-stationary condition, that means that the pickup ion density here on the left is just balanced by the ion production rate. So we have the neutral particles times the ionization rate. And if we consider these two to be balanced, we can estimate these neutral particles. So omega t here below this in the denominator, yes, is kind of the characteristic time scale. So you can think of how many gyrations of these particles are necessary to give the complete energy from the ions to the waves. So after that time, the complete energy of the pickup ions are lost to the solar wind, to the wave itself, and this particle is completely embedded in this Maxwellian solar wind once again. And from computer simulations, we know that it takes about 60 to 100 gyrations. That this wave is completely excited. So, yeah. The photoionization rate, and I do not need to tell you, varies significantly from our solar wind activity as well as the distance of Mercury to the sun. So what we did, without going into detail, we estimated the solar flux index from a database at the Earth, and then we scaled it to Mercury itself. So with this one, we get now the lithium density. Once again, we have put into this equation, we find it here. So as a summary, from the magnetic field measurements, ionization rate and solar wind propagation model, we get all the values at the time of observing the event itself. To estimate this density, we need two assumptions, two more. One is that this characteristic time would be 100 gyration periods. And the second is that about 30% of the free energy is transferred to the waves itself. So this is a very conservative assumption, as well as this 30%, because it could be also from computer simulation shown down to 10 or 5% as well. Okay. And that's the result. So on the y-axis, we find the lithium number density along the distance to the surface, so the radial distance. And here are our 12 events plotted at points. And what you find actually, each of the events are very individual. That means to a specific time we observe this event and then we do not see anything, except that one in April 2 and 3. That means something must be happened during that time. However, we looked into our data set. Once again, if a CME hit Mercury or whatever, nothing was there. So we came up one step up. Yeah. How many times now?
10.
10 minutes?
So 5 minutes.
Make 10. So then I speed up the things a little bit. Now the data point itself, once again, the equation from before, there were lots of assumptions, lots of uncertainties. We used propagation models and so on and so forth. So what we did is a Monte Carlo error propagation, where each of these parameters from before is assumed to have an error. And then we just used our equation, had a kind of a normal distribution of the different parameters from above, and just applied it to this Monte Carlo error propagation to obtain an error. And this has been done for each event individually, and in the end, it turns out that this the error bars of the events might be within 1 order of magnitude, which sounds massive, but don't forget, this is the first observation with lots of assumptions, and we need to account for these assumptions. So the error bar needs to be in this case. So this is the 95% quantile, by the way, from the Monte Carlo error propagation. Okay, so where does this lithium originate from? This is the question we are all after. So I mentioned this before, 4 processes. So the first one was this low energetic processes or the high energetic process. Which of these 4 might be the case? So once again, here are the thermal evaporation and the photostimulated. Just put it in one. To study this, we used a Chamberlain exosphere model. This is a model to reproduce the ballistic trajectory of particles in the exosphere, for example. And this is widely used at Mercury. And so we adopted this simple model, which is based actually or determined solely by the initial density and thermal velocity at the exobase. That means on the surface at Mercury, in case of Mercury. So only based on the temperature and the surface density, we get kind of a trend density profile of the different species. So if the temperature gets higher, then this curve actually flattens out a little bit, gets more horizontal. If the temperature gets lower, of course, we go down. This is our starting value. Then on the y-axis, we move a little bit to lower values. Okay, so now we could actually use this Chamberlain model with a average surface temperature of 450 K. Okay, this is one parameter, starting parameter, and also a surface density we need to do. And we assumed in the beginning that this density is based on the upper limit of the surface density based on the non-detection of this species. So in previous publications, it was considered that the surface density needs to be lower than this value, otherwise we would have had observed it. So if this density would be 10, we would have seen these spectral lines. We didn't see it, must be below this value. Good, if we plot this Chamberlain model now into our, we are far off. So none of those lithium densities can be represented by this model, which immediately excludes, because we cannot move this line more to the right, otherwise the density would increase to values where we would have had detected it. So we can actually rule out such low energetic processes. Okay, so 2 left. 5 minutes, huh? 2 left. First, let's have a look at this iron spire. Energetic process first. So now I'm a little bit in error. So energetic processes, that means for energetic processes that this temperature needs to increase, dramatically increase. And in fact, okay, first the iron sputtering, sorry. So iron sputtering, that means we have energetic particles hitting our particles out of the surface of the river. So the solar wind, these particles may come from solar wind or from a magnetic reconnection, daytime magnetic reconnection. These energetic particles move along the magnetic field line, hit the surface, and kick these particles out. But this is very unlikely because we detect these events very rarely and very sporadically. And this reconnection, as well as energetic particles in the solar wind, are actually always there. So we would have, we need actually to have more observations of this, that this can be really a process that could explain our observations, but we do not. ICME, so interplanetary coronal mass ejections, might be also responsible for sputtering. However, during our observations, we check the catalog. There's a complete catalog. We do not find any ICME which really occurred during the observation of these events itself. So we can rule this possibility also out. So what's left? The meteoroid vaporization. This means high energetic impacts mostly explain these events. Okay, then we test this. So that means, first of all, we have a sporadic occurrence, short duration. That means or fits very well to heavy meteoroids, which hit the surface rarely, occasionally, and then produces massive ejecta from the surface and the material from the meteoroid itself. So this might explain this best. So we know from previous studies, so from hypervelocity experiment as well as from experiments on observations on the moon, Earth's moon, that these meteoroid impacts create clouds, vapor clouds between 2,500 to 5,000 K. So we take now for our Chamberlain model just the average value. We go for the middle and applied this one a least squares fit to each of our error bars, to the upper and lower one. And this is done to each of the events. And then we averaged this whole thing out. Means we took actually the median of all of the upper and the lower error bars. And so we end up with a surface, or average surface density range between 0.02 or 0.03 to 0.2 particles per cubic centimeter. And indeed, if we have this median value, we see that all of our events fall within this range itself. And so this would be also another evidence that we are not so far off this temperature of kind of 3000 Kelvin, which would be explained once again by this meteorite impacts. By the way, if we change these values to 2500, this curves just a little bit down. If we go to 5000, maybe a little bit up. So there is not a dramatic change in between those two values. Okay, so where does it originate? And this is really the last slide. Thank you. Maybe a small. So once again, back in the envelope calculation. So in ordinary chondrites, which is kind of, Helmut, please correct me, 80% of the meteors have this ordinary chondrite meteors. We find that the lithium to sodium ratio is about 10 to the power of -4. So 4 times more sodium than lithium in these meteorites. Sodium in ordinary chondrites has a kind of a 0.68 percentage in this, so the average atomic percentage of sodium in these chondrites is 0.7%, roughly. And at Mercury's exosphere, and sodium has been studied for decades already and very much into detail because the sodium spectral lines, the D lines, can be distinguished very precisely due to the nature of the D lines. And so the content of mercury is estimated to be 2.1%. So that would mean that if we assume that the lithium or that the sodium, so the large sodium content itself is explained by the fact that lots of meteorites, micrometeorites, over billions of years delivered this sodium content onto the Mercury surface. If we now assume that the lithium, which is also in this ordinary chondrites, of course, also enrich Mercury's lithosphere or the regolith on the top, then the lithium content on Mercury would be approximately 6 particles per million. However, the lithium content of the impacting meteorites is only about 2 particles per million. And now we see that actually there would be a factor of 3 difference in between these two. And this means the following. Actually detected in our events is not only coming from the meteoroid vaporized and we detect the lithium. No, meteoroid hits the surface, evaporates, and also ejects material from the surface out into the space. So the lithium found here is primarily originating from the planet's surface itself. And this is really the summary. Just to illustrate this in a nice way. So once again, here's Mercury with the solar wind interplanetary magnetic field bow shock. We have a meteoroid, of course. This is kind of a three-dimensional view. So the meteoroid is massive. It's going towards the planet. At the planet, we have this ejection I just explained. So evaporation of the meteoroid itself, as well as the surface material. In this material, we also find this lithium particle. These lithium particles are photoionized by the solar radiation, UV. Gets ionized, so charged. Charged means it gets picked up by the solar wind. Once again, this surplus of energy of these pickup ions is transferred to the so-called ion cyclotron waves. These ion cyclotron waves are subsequently observed by the messenger spacecraft and explains this whole scenario. Okay, thank you very much.
Well, thank you for explaining that. The questions. Let's start with Peter.
I have a question to the kind of stochastic nature of these waves. I mean, when you say that the lithium density is this value, you would, suggest that this is always there. But then you also explain that probably why you have sometimes an event and often you have nothing is because it's a stochastic thing from these events. So I wonder if it would be actually something more stationary. What would the messenger have measured if there would be just a constant density? So you have always this energy available to amplify waves in a certain frequency.
Not only the energy, actually, you need the particles itself as well.
Yeah, say you have constant particles available.
Okay.
What would the instrument see?
So actually, we did this. So the idea of this technique of spectrometry, using the magnetometer as a spectrometer, particle spectrometer, comes from the fact that we had a look at incompressible waves and found out that those waves came from the pickup of hydrogen, atomic hydrogen atoms. And this atomic hydrogen are very light compared to the lithium, of course, 7 times lighter, and can reach to this extended altitude. And we have much more hydrogen than lithium atoms. So this lithium, exactly the scenario you presented now, is permanently there, is refilled or thermally released from the surface, and always fill up this extended exosphere of Mercury. Gets photoionized, excites waves, and so on and so forth. And in fact, we found over 4,000 or 5,000 of these pickup ion cyclotron waves for hydrogen.
But it means that actually it's not the reason for the stochastic nature is not the events of the impact. It is more something that happens in this amplification of the waves. So even if everything is constant, so the solar wind is constant, the lithium density is constant, you would still have events, right? But sometimes it happens and sometimes it don't.
I think the lithium should be always there, but it doesn't reach these distances and so on without such events. And the densities are very low, even less than here. And with BepiColombo, probably when you're closer to the surface, you may probably detect it with another instrument, like with the mass spectrometer, which are in Pica.
Depending on the geometric factor of the instruments, yes, might be.
Yeah, because I mean, it depends also that you reach these altitudes, you need a big, relatively big, not micrometeorites alone cannot deliver this. And the micrometeorites are always there, but they do not produce such huge clouds that it can be detected by this method.
In fact, actually, we determined how big this meteoroids needs to be, and we found kind of 10 centimeters up to 30 centimeters. Yeah, I think. Was it more? I'm sorry.
What you need is the ion and the coupling to the magnetic field, right? This is literally what
So the resonance condition, yeah.
Yes, exactly. So that means if your magnetic field, if one could imagine that the magnetic field is not as laminar as this picture now suggests, and that due to the turbulent or the local inhomogeneous nature of the magnetic field, that this events could then be excited. So this goes a little bit into that direction, right? You have a constant background, but what you actually only need is an event that makes it visible.
Yes.
And it could either be a super meteorite or an inhomogeneity in your magnetic field. Is that right?
No, it's with the
Okay.
so maybe there's a little misunderstanding. So in fact, you're right. You need the right background conditions that these waves get excited. Very true. So kind of if you have a CME, then probably those waves will not emerge. Then also, this is like a zoo out there with plasma waves. So one eating the other one. This is similar to an ocean or on the sea. You see lots of small waves, but some waves grow bigger, other ones get smaller. And exactly the same is in the solar wind itself. So you have always these small fluctuations. And in our case here, we have some kind of incompressible fluctuations. These ones get through the existence of this lithium, of this ionized lithium, through this existence, they get excited actually and get the energy from this pickup. Explained. But you're right, of course, if it's a very turbulent thing, then probably we would not observe the events.
And there also has to be a certain amount of particles that get picked up.
Yeah.
So if it's just one ion, then
So
there's but I don't think we know what it is.
This is the challenge. I mean, lithium always around. It's basically then what makes it visible. Either the argument is you have it, I need something to kick out the lithium sporadically, as you have suggested, or you have something to make the lithium visible through whatever, to the fact that it reaches the resonance.
Now I understand you.
Resonance state.
Yes, actually, yes. So if we think about the background condition, then the background condition only 12 times in 4 years have similar thing. Actually, the solar wind, I mean, of course it's different, but this is very sporadic. So
it's not a criticism at your work.
no, it's good actually. This is how science should work actually.
The thing is, if that is true and you have this amplification only when there's a particularly large density of lithium around, then you would overestimate the total content of lithium in the whole thing because you picked up this 12 events where this density was super enhanced. I think we are not. We're not thinking this is true, right?
No. So from this back of the envelope calculation I presented from before, we actually just say in the conduits we have this content from the sodium, so it's lithium to sodium ratio. Okay. Sodium, we are very sure about the percentage, so this is very well studied. And we expect that lithium, if this is delivered by the meteorites, we have had the same ratio then. Yeah, we can talk about it.
I guess you have a lithium source in addition. It's the spacecraft itself. How can you prevent, for instance, the outgassing of the lithium battery on the spacecraft?
So I guess this would be way too few elements that would outgas and to excite the wave itself. Yeah.
Do people also find the similar thing at the moon?
No.
You know, lithium, you have the meteor. If I take the bunch of this picture, if I take the bunch of off, it's a like solar interaction with the moon.
Sure.
Feature.
Exactly.
So meteoroid hit the moon. Anybody work on this?
I'm not Artemis.
Very,
So many data.
there's only one paper from Artemis that shows some evidence of cyclotron waves around the moon. It's
No, not with lithium.
No. That was just proton cyclone waves, and there's nothing else at the moment.
And Tilong, don't forget the magnetic field at the Earth's orbit is kind of factor 10 times lower than at Mercury. So that means that the gyro frequency of these particles is way larger. Okay, the radius way larger. So we need also the right amount of background magnetic field to really trap them into this circular motion to capture them. So this is also the reason for Jupiter's moons or Io, for example.
At Io, you have the constant volcanic activity, and there I see about 8 or 9 different species.
Yes, and molecules even. So, yeah.
I was going to say, why do you expect the lithium to be in atomic form? I mean, I guess in the meteorite is like in carbonate and so on, right? It's mixed.
No, this is only
detected, and only a small fraction.
3000 or let it be 2000 Kelvin is quite an energy. I don't know. I'm not a geologist or meteorologist. Yes. Might this temperature might be enough to release it? No.
Most of it is anyway coming from the surface, right? So I think it would be enough to release it and to have it in atoms. I also have a question.
Yeah.
I think that the size of the meteorites was around 10 meters, not centimeters.
Oh, yeah.
And I'm wondering whether the mapping instruments of MESSENGER would have a high enough resolution that one probably could find the new impact craters.
Yes, this is a good thing, of course, and they do in fact. So they observe the surface and then compare it with other pictures from the same area and then really attributed some of the meteorite events. So in this case, there is a list, complete one, and a complete and preliminary list, let's say, and we checked with the dates, but due to during that times where we observed the events, unfortunately, we couldn't attribute it directly to impact.
My question is a common question. So is this the only method we can observe lithium in the exosphere?
No. So
why?
This is a question actually for our instrument teams here, for particle instruments. If the geometric factor of the particle detectors, of the particle instruments would be high enough, then you could...
Yes, but the geometric factor would not dramatically increase the density.
Probably.
And another thing is the impact. I understand the logics behind the impact, but the impact is like an explosion for high energy. And if the argument is that in the impacting bodies there is not enough lithium, the explosion is the compression and making into small volumes larger number of lithium. So, and if this material is somehow emitted to space, it probably would not be very homogeneous. It would be bunches of material in which the lithium concentration would be larger.
It might be that there are actually branches where the lithium content is higher. Yeah, sure.
Bruno?
Just go back to your second slide. A basic question. You mentioned 3 different processes.
The 4 different processes.
4 different processes, yeah. Yeah, this one. Which one is producing ions and which one is producing neutrons? That's my question, because if you produce ions, aren't they kept with the magnetic field?
Exactly, they wouldn't reach out to the
yeah, that's my question.
Exactly, they would kept there. Yeah.
Because on the left-hand side, the low energy process seems to me is ionizing, yeah. Because just a few kilometers outside, you say the photon is ionizing the lithium. So why shouldn't it ionize then on the ground?
Oh, this photon I'm not an expert in this, really not. But this photon stimulated desorption is kind of you really release complete elements from the regolith itself. So the binding energy is overcome between the elements or the molecules, I guess. Similar like the photoelectric effect we see. So if the h nu, so the frequency is high enough, then we can release lots of this particle. If not, then not. but I'm not an expert in this.
You're not ionizing them?
As I said,
Energy?
I can't repeat, I don't know.
You would need to ask Helmut, I guess.
Yeah.
Maybe.
Oh, sure.
The last question from you.
Where is the lithium coming from? So I'm actually kind of surprised that the surface of Mercury has lithium. Where does it coming from?
Yes, and I noticed that this was not emphasized enough here during this presentation, but the scenario is to follow that over billions of years, micrometeorites and other meteoroids, bigger meteoroids, actually was hitting the surface, similar like in the Earth. You also have all the time info. And this material is actually on the surface, accumulates on the surface to some extent.
It's basically produce a electrolyte. The electrolyte is basically pulverized meteorites. Okay.
So you have kind of on the moon, you are not on the rigid body, basically you're on sand.
Yeah, I know it.
So it's a similar.
Yeah, okay. So it's basically pulverized meteorites. Okay, cool, thanks.
Yes. So the hypothesis, once again, nothing is in stone, so yeah, we could put.
Okay, thank you for your attention. Danile will be still here for the next 20 years. So